Welcome to 1D Kinematics Acceleration. Acceleration is defined as the rate of change of velocity. It is how quickly an object's velocity changes. So remember when we were talking about velocity, it's how quickly the position changes, and here it's how quickly the velocity changes. And acceleration is that a vector or a scalar. You can see it has a hat on it, and so that is a vector. And so we have acceleration is how quickly the velocity changes. And whenever we do like a change, delta of a v, it's going to be v2. We always do 2 minus 1, right? So our change in velocity, v2 minus v1, over our change in time, t2 minus t1. Or more simply, we can just use the delta value on both the numerator and denominator. So go ahead and add this equation to your equation sheet. Acceleration is defined as the rate of change of velocity. It is how quickly an object's velocity changes. Oh, that's just the same thing. So here's an example of the units. We do a unit analysis. So here we have, when we're talking about velocity, the units are meters per second. So meters per second minus meters per second is going to give you meters per second. If you have 20 meters per second minus 10 meters per second, you'll result with 10 meters per second. So the units on the numerator is going to be meters per second. And then on the bottom, we have like seconds minus seconds. So if we had like 5 seconds minus 3 seconds, you would end up with 2 seconds. So you can see that we have seconds on the bottom and meters per second on the top. Well, if you take meters per second divided by seconds, it's meters per second, it's actually going to result in meters per second squared. So the units for acceleration is meters per second squared. Make sure that you also include the units when you're writing the, maybe you want to add the SI units when you're writing in the equations. Okay, the units of acceleration are meters per second squared. The units of acceleration may look odd at first, meters per second squared. This is a shorter way of writing meters per second per second. If something changes, if the velocity changes, if 10 meters per second every second, that means that if it started at 0 meters per second and it was changing 10 meters per second every second, that means that 1 second it'd be 10 meters per second. At 2 seconds, it'd be 20 meters per second. The change is 10 meters per second every second. Acceleration is the rate of change of velocity, how much the velocity changes every second. Acceleration takes its direction from the change of velocity. Since the initial velocity and the final velocity could be in different directions, it is important to define which direction is the positive direction. And there'll be some examples. So here, forward is typically positive and backwards is negative. Using a compass, typically north and east are positive directions and south and west are negative. You do not need to always use this convention. For subproblems, it would be logical to set south or west to be positive. Just make sure that when you're writing the equation, you're clear and that you keep things consistent. To solve an acceleration problem, you will need to know 3 values to solve for the 4th. Look out for the key phrases like from rest or to a stop. These tell the velocity without using values. For example, a horse begins a race from rest. That means its initial velocity is 0. And it has an acceleration of 2.2 meters per second squared north. What is the horse's velocity after 5.8 seconds? So here, if we look at this, you can see that our acceleration is 2.2 meters per second squared north. Our initial velocity, or v1, is 0 meters per second. Our change in time, because initial time was 0 and final time was 5.8. So our change in time is going to be 5.8 minus 0. So it's 5.8 seconds. And it's asking for the horse's velocity after that. So it would be the final velocity, or our v2, right? So this is our question mark. It's always good to write out all the knowns and unknowns, and then you can find which equation would best be used. So here's our equation. Acceleration is our change in velocity over change in time. And we can rewrite this. So here we're looking for v2, right? So we're trying to solve for this value. So in order to do that, we need to do some algebra. So we can multiply both sides by delta t, right? And we would get a delta t, and these would cancel. So we would be left on this side as v2 minus v1. Now to get v2 by itself, we would need to add v1 to both sides, right? And so now we would have a delta t plus v1. I should do little squares, right? Little hats. Is equal to v2. So now we can solve for our v2 by plugging in the other values. So we put 2.2 meters per second squared north times 5.8 seconds plus 0. That's going to give our value, which is 12.76 meters north. And that's the final velocity. Now, is this final velocity, do you think this is an instantaneous velocity or an average velocity? This would be an instantaneous velocity. Here's another example. A hockey puck with an initial velocity of 65 kilometers per hour west. So our V1 is 65 kilometers per hour west. Ricochets off the boards. So there's the board. The puck comes in at 65 kilometers per hour. Oopsie, I should probably draw it with the accurate look. It's heading west, right? So here would be the boards, and the puck would be traveling this way, 65 kilometers per hour west, because, you know, here we have, this would be west. And so it hits the board, and after 0.76 seconds in contact with the boards, its final velocity, then its final velocity is going to be 47 kilometers per hour east. Okay, so this is it continues to go at 60, you know, it's not really slowing down. It's going 65 kilometers per hour. It's going 65. The change in the velocity happens when it's contacting the boards. And so it, you know, it happens very quickly. But the boards slow it down to a stop and then pushes it, basically. And so then it springs back at 47 kilometers per hour. So let's write down the things we know. So we know that the initial velocity, like we said, is right here. And we know that the time in which the velocity is changing, so the total time in which the velocity is changing, is 0.76 seconds, where there's contact with the boards. And we know that its final velocity is 47 kilometers per hour east. And it says determine the acceleration of the puck. Okay, so knowing all that, we have, first we can define, I'm not sure how I got that up there. Just move that away. We can change our units to meters per second. That's what they did here. So they took kilometers per hour. They multiplied it by, there's 1,000 meters per kilometer, and there's 3,600 seconds per hour. So you can see we have their kilometers cancel with our kilometers, our hours cancel with our hours, and we're left with meters over seconds. And if you multiply this out loud, you get 18.05 meters per second. And of course, the direction is going to stay the same. You can do a similar thing for V2. And so if we plug this into the equation, we get 13.05 meters per second. And this is going east, remember? And remember, east, we said, is positive. So this is going to be, because it's east, this is a positive sign. And if east is positive, then west would be negative. So therefore, since this is positive, this is negative, this is going to be a negative number. So minus, because we have V2 minus, this is that minus, and then we have a negative 18.05. So when you plug that in, you end up getting 40.9, which rounds to 41 meters per second squared. And Was this a positive or negative number when we did this? It was a positive number. So that's going to be in the positive direction, which makes sense. If we always need to go back and think, does it make sense? It makes sense because the acceleration was in that direction, which is east. Okay? That's it for acceleration.